Hi everybody. So this is going to be kind of where I left off in the notes in chapter 16. I'm going to probably cover 9 or 10 slides in each of the videos. You've got to remember to stop and pause the videos and work on problems. Maybe listen to me explain it before you write anything down, and then pause the video and go back and try and do the problem yourself. Okay. This isn't an ideal setup. I'm hoping to get this a little bit smoother as I go on. For now, I've had to write on the slides first, okay? And so I won't be solving them at the same time as you. You're going to have to kind of look at them and listen to me explaining them. So we're going to work on calculating pH. Now, some of you, the night class, we already did a little bit of this, but in the day class, this is about just where I left off. So we're going to be talking about how to calculate pH first for strong acids and bases. And remember, what's unique about strong acids and bases is that they completely dissociate in water. And so that means if I know the concentration of the acid or the base, I know the concentration of the hydrogen or the hydroxide ion. So we're going to look at an example for an acid and a base. So we'll start with hydrochloric acid. We'll say that we have a 0.001 molar solution of HCl. I've written a dissociation reaction there. So you can see that the HCl breaks apart into hydrogen and chloride, one-way arrow. And what that means is that if I have 0.001 molar HCl, I have 0.001 molar hydrogen ion. So I know the concentration of my hydrogen ion, and then I take the log and change the sign, and I get a pH of 3.0. So if I'm going to do this for a base, we're going to do the NaOH. So the NaOH, I've got to do the same things. So pause it, try and do it. So the NaOH breaks apart into sodium and hydroxide. What's different this time is that I know the hydroxide ion concentration, not the hydrogen ion concentration. And so when I take the log of the 0.001 and change the sign, what I'm getting is a POH, not a pH. So in order to find the pH, I have to subtract the POH from 14, and it ends up being 11. Now try it, see if you can do this for the calcium hydroxide. Pause the video. So CaOH2 goes to calcium ions and 2 hydroxide ions. So my hydroxide ion concentration is twice as big. All right, so now my POH this time is 2.7, and then my pH ends up being 11.3. So slightly more basic, 11.3. You notice it's twice the concentration, but it isn't twice the POH, okay? So you got to remember that we're working with a log scale here. This is just a picture that shows you a bunch of different materials you might run into around the house and what their hydrogen ion concentration and pH values are. Some of these things might surprise you at how acidic or basic they are. Bleach, a lot of times people don't think of as being basic, but it's very basic. Soda, between 2 and 3. Rain even. So let's talk about weak acids. So calculating the pH of a weak acid is very different. Okay, so by definition, a weak acid is not completely dissociated. So I don't know what the hydrogen ion concentration is just simply by knowing the concentration of the acid. So what I need to do is treat it like an equilibrium problem. I want to write an equilibrium expression, look up an equilibrium constant for it. So this is a listing of several equilibrium constants for acids. We call these dissociation constants, and we give them the symbol Ka. So this Ka is what we'll be using when we talk about an equilibrium constant for a strong acid, for a weak acid. All right, so this is just showing you a bunch of different acids and what their equilibrium constants are. And you can see that they're all pretty low, okay? So we're going to do a problem. So we're going to start with this idea where we would calculate the pH of a 0.010 molar solution of acetic acid. So first thing I do is write the dissociation reaction. So you can see I've written it there. And then I set up an icebox. And so in my ice box, I've started with my starting concentration of the acid as my initial. I assume that the hydrogen and the acetate are 0 to start with. And then I say, as we did before in Chapter 15, I'm going to let X equal the change in the hydrogen ion concentration. So I filled that into my ice box. And if the H plus gains X, since the acetate also has 1, essentially they're the same, it also gains X. And the acid loses X. And so then I calculate what I have left. I've got equilibrium concentrations for the hydrogen, the acetate, and the acetic acid. Okay? So I'm going to continue this on. So we're going to write an equilibrium expression. So we write an equilibrium expression, products over reactants. So I've done that. And I look up the Ka value. So the Ka value is in Appendix D. That's on page 1126 in your text. You might want to make a copy of that and keep it around when you're working on these problems so that you can look at them. And now I'm going to make an assumption that we didn't do before. So what I'm going to assume, and this is a good assumption for most weak acids, I'm going to assume that the change in the hydrogen ion is actually very small compared to what I started with. And so that's what this is saying here. It says assume that X is much less than 0.010. That's usually a good assumption because of this. Okay, so this 10 to the minus fifth, when I look at that, that's a really small number. And so what that means is the acid doesn't break apart very much. And so the amount that would turn into hydrogen ion is pretty small. So when I make that assumption, then when I plug into my equilibrium expression, so my acetic acid concentration that I took from the table, instead of saying it's 0.010 minus X, I can just say it's whatever it was when it started. It's 0.010. So I solve for X squared. I get 1.8 times 10 to the minus 7th. That's the wrong number. I forgot to change that. Sorry. That's a 7. And then I take the square root, so I get 4.2 times 10 to the minus 4th. That is my hydrogen ion concentration. That's the way I labeled it in my table. And then I take my minus the log of that to get the pH. So I get a pH of 3.37. So notice 2 decimal places because there's 2 sig figs in this number. Okay. So we're going to try this again. All right. So what I would suggest is that maybe you look at your slide, maybe pause the video, see if you can do the next problem. All right. And then I'm going to show you how to solve it. All right, so I'm going to have to pull this recording down a little. It's kind of blocking some things. See if I can expand this or not. All right, we'll have to go down to the bottom afterwards. I'm going to move myself out of the way here. So we're going to calculate the pH of a 0.010 molar solution of hypochlorous acid. So I looked up the Ka, I wrote the equilibrium expression, and then I set up my ice box. So I've got my initial, oops, I lost my pen, guys. All right, so I've got my ice box here. My starting concentration is 0.010. The hydrogen and the hypochlorite ion are both 0 to start with. And again, now I'm going to assume I'm going to let X equal the change in the H plus. So I put that in here. Then my ClO minus is the same. And so I'm left with X and X and 0.010 minus X. Then I plug back into my equilibrium expression. So that's what I've done down here. My Ka is equal to X squared over 0.010. And again, because I assumed that X was very small compared to 0.010, I replaced that. So I got X squared is 0.010 times 3 times 10 to the minus 8. X squared is 3 times 10 to the minus 10th. And then let me pull this down so you can see the bottom of it. So then I solved for X. I just took the square root, 1.7 times 10 to the minus 5th. And then I ended up with a pH of 4.76. So you want to try and do these problems like over and over again. Just keep trying to work on them. Try and figure out how to do them a couple times. I am going to be having virtual office hours too, so you'll be able to like either Zoom with me or maybe collaborative Blackboard. I'm working on that. All right, so now we're going to try and do this problem backwards. All right, so you might want to watch this before you try and do it. But this says that you start by making up a solution of propionic acid at a known concentration, essentially. And instead of assuming what the hydrogen ion concentration is going to be and using the Ka, what we're going to do in this problem is to measure a pH and know what it is and calculate a Ka. And this is exactly what you're going to be asked to do in the lab, in the equilibrium lab. We'll be giving you concentrations and then measured pH values, and you're going to calculate the Ka. So when I do this, the first thing I want to do is to start by calculating the initial concentration. So that's what this first step is here. So I took 0.4625 grams and divided it by the volume, and then changed grams to moles. So I got moles per liter. I got a molarity that way. Then I wrote my equilibrium reaction, and I used my starting concentration as the concentration of the propionic acid. Zeros for the other two. Now what's really different is that instead of letting X equal the change in the hydrogen ion, I calculated it based on the pH. So if I know the pH is 3.24, then the hydrogen ion concentration, I change the sign on the pH, and then I take the inverse log. So it's 10 to the negative 3.24, which is 5.75 times 10 to the minus 4. So I took that value, and it made it the equilibrium concentration of my hydrogen ion. So if I started at 0 and I ended at that, that's also my change. So then I'm able to essentially calculate what the value of the propionate ion is, as well as what the value of the acid was at equilibrium. I plugged those numbers back into my equilibrium expression, products over reactants, and I calculated a Ka value. So when I simplified that, I got 1.36 times 10 to the minus 5th. So one of the other things that we're going to talk about in the lab is percent ionization. So talk just kind of briefly here now about what percent ionization is. So percent ionization talks about how well the acid is ionized. So we know that weak acids are only partly ionized, and what we want to know is what percentage of the molecules are broken apart. And it turns out there's two things that affect that. So one is the concentration of the acid, and this would be for a specific acid. So as the concentration goes up, the percent ionization goes down. The other thing that affects it is the Ka itself. So when I change from one acid to another, the percent ionization changes. So as the Ka gets bigger, the percent ionization also gets bigger. If I want to calculate a percent ionization for an acid, basically what I'm going to do is I'm going to use the value that I have for the H plus concentration and divide it by the initial acid concentration. So back on slide 30, oops. I kind of lost my spot there. So back on slide 30, we calculated the H plus concentration of the acetic acid in a 0.010 molar solution to be 4.2 times 10 to the minus 4. So if I want to know the percent ionization, I put that value in and I divide it by the starting concentration. And I end up multiply by 100 and I get my percent ionization. So my percent ionization in this case would be 4.2%. So this is a calculation you'll be doing in the lab as well. All right, so I think we'll do this problem next time, okay? So I think I'm gonna kind of pause here. Remember to stop and go back through the slides and try these problems as many times as you can. Bye-bye, guys.